What is the reproductive number? It's just the number or the average number of successful transmission per infectious person. Generally, we have two conditions. First, we have a totally susceptible population. The black humanoid here is susceptible, the red is infected, and the green is immune, meaning that protected from infection. So in this population here, everybody is susceptible. No one, we don't have anyone here who is immune. In this case, when an infection starts, we can talk about the basic reproduction number. So it's what is the average number of people who will become infected when an infectious person enter in a population where everybody is susceptible. This is called the basic reproduction number. It is generally noted like this, R with a 0 subscript, and they usually call it R naught. For example, the SARS in 2003, we could measure their basic reproductive number because everybody was considered to be susceptible because it was the first outbreak. There are cases where some people in the population have immunity against the disease. So in that case, we don't talk about basic reproduction number, but we talk about effective reproduction number. And the effective reproduction number is just the basic reproduction number multiplied by the proportion of those who are susceptible. Mathematically, R naught, or the basic reproduction number, is the transmission rate times the duration of infectiousness. We can further break the transmission rate. The transmission rate is composed of two elements. We have the contact rate, which is the rate at which people get contact one another, and we have the transmission probability. What is the risk of a person A to transmit the infection to person B whenever there is a contact? And most of the interventions in public health, interventions to control infectious diseases, most of them will target either one or a set of these elements here. For example, when we do isolation of cases, generally referred to as quarantine, generally we are decreasing the rate of contact. When we decrease the rate of contact, we are decreasing the transmissibility of the infection. We can look at some other interventions that are implemented to control the probability of transmission. For example, the use of condom. When we use condom, we decrease the probability of transmission. In that way, we decrease the transmissibility of the disease. Antiretroviral therapy for HIV-infected people. When you take it, the number of virus in the blood will decrease. So in that way, you decrease also the probability of transmission. Vaccination, any kinds of prophylaxis we use, we are playing on this factor here, or even treatment. The duration of infectiousness. Some infectious diseases can be treated by antibiotics. When you treat, you decrease the duration of infectiousness, you stop the transmissibility. So most of the interventions will be playing on one or many of these factors here in order to control the infectious disease. But what does it really mean practically? R naught of 1 means that one infectious person can give infection to only one new infected person. In that case, we have an endemic stage because only one person can transmit the infection to another one, only 1 to 1. When R naught is more than 1, it means that one infectious person can transmit infections to more than 1 people. In this condition here, we can have an epidemic because more and more people will be infected and then become infectious. Then when R naught is less than 1, one infectious person transmits to less than 1 people. So we have a possibility here of seeing the epidemic dying off. How do we measure that? For example, here, let's assume that the primary case is this one here. It could transmit infection only to 1 person, so he has transmitted to 1. Here, the secondary cases could transmit to 2 people, so he has 2. This one here could not transmit to anyone, so 0. He could transmit to 1, so on and on. And then when we take the average of that, we can have the basic reproduction number. For example, here it's 1.5. 1.5 tells you that the infection will continue on and on and on because it's more than 1 in this scenario here. More illustration. We have an R naught of 1, meaning that 1 person can transmit infection only to 1 person. For example, this one here becomes infected, and it goes on and on. But we will have an endemic stage. The epidemic will not take off, but we will have a stage where the epidemic is there, it's not taking off, it's not dying off. In this scenario here, the reproductive number is 2, the basic reproductive number is 2, meaning that 1 person can transmit infection to 2 people. So in this case here, it goes like this, it goes, and it goes. So as you can see, the more we go, the epidemic spreads very rapidly. So we have here a risk of epidemic. But let's look at this scenario here. In this scenario, we have some susceptible, but we also have some people in the community who have immunity, so they cannot develop the disease. So we have an R naught of 3. This means that 1 infected person can transmit infection to 3 people. So here, it could transmit to 3, but the 2 here are resistant because they have immunity. They cannot become sick. Only 1 here is susceptible. In that case, it's only that 1 who will become infected. And in the next transmission round, this one can transmit to 3 because the R naught is 3, but he had contact only with those who were immune, meaning that the epidemic stops here. So what does it tell us? It tells us that even if the R naught is more than 1, if some people in the population have immunity, the infection may or may not take off, depending on how many people in this community have immunity. And you can see that some people here, they are susceptible. They can become sick, but they didn't become sick even if they were not immune. They were protected by the people who are immune. So people who have immunity in a population actually protects people who don't have immunity. That is why it's not important when it comes to vaccination. It's not important to give vaccine to everybody 100%. You just need to give vaccine to a fraction of them, and the other one would be protected indirectly. And this kind of indirect protection is what we call herd immunity. It's the protection that people who are susceptible in the community get from people who are immune. So it is called herd immunity. This is example here. Let's look at it in a big slide. This showing the expected number of cases for polio vaccination in the US between 1958 1961. So it shows the expected number if the vaccines protect only those who receive the vaccine. We will have this number of reported cases. But in reality, the number of reported cases was much lower here. So this means that some of the people in the community who didn't receive the vaccines were nevertheless protected by herd immunity. So herd immunity is a very, very important concept. And this is a very important concept that is used in immunization and vaccination programs. You want to know how many people in the community do we have to vaccinate in order to protect everybody.